Welcome to the Module 2 lecture for CET 208, Concrete and Asphalt Materials. Let's move on and we're going to take a look at the compaction part of this presentation. And what are we going to look at? We're going to look at the maximum dry density. We're going to look at the field density, the compaction operations and quality control. And we're going to take a look at some test procedures that we would use. So what is compaction? Compaction is the densification of soil or a soil by reducing the air voids within the soil by the application of mechanical means to compact the soil tighter and tighter together because we want to get greater strength and durability out of it. So we have to keep in mind that once we disturb a soil, we start doing some excavation work and things like that, we've now loosened them up. And I know that we've all dug holes and put the sand off or dirt off to the side, and then we go to fill the hole back up and we've got more dirt than we started with. Well, that's because it's broken apart now and it's expanded. So we want to try and get those particles to go back together again. So they got to start moving in and filling these voids. So we use mechanical means to do that. Of course, compaction is used throughout the construction industry. Of course, we see it a lot with roadway designs, but we also see it with driveways, curbs, sidewalks, anything like that that are being put in. You'll see maybe some small vibrating machines, flat plates that come in to get them soils to try to get them as compacted as we can because we don't want cracks or bad settlement problems to occur. And of course, as we know, really with highways, we get the embankments, earth dams. Again, we want to have a stable foundation for the life cycle of the completed project. And again, we're looking with compaction to mechanically force loose soil particles together in order to improve their strength by increasing their unit weight per volume. And of course, when we discuss the degree of compaction, we are measuring its dry unit weight based on the design parameters that have been established by the design professionals. And we have to remember that it's never going to be. So what's the overall goal of compaction? What are we trying to do? And the main objective of compaction is to improve the soil region or subsurface area's density and other properties in order to reduce settlement concerns. We want to get those soils to push back together as best we can, get rid of those voids, and have that where once we start to put a load on it, the soil will hold it. By increasing a soil's density profile, we can improve the soil's strength and lower its permeability rates in order to control these future settlement concerns that we may have. Compaction increases the shear strength of the soils, while at the same time increasing the bearing capacity of the foundation system, supporting the structure's design. Also, compaction decreases the undesirable settlement of the structures, provides a reduction in hydraulic conductivity activities, while at the same time increasing the stability of slopes on embankment designs on highway and roadway transportation systems. So again, the main objective with compaction is get them soils back together. We're trying to force them back together as best we can so that we don't have these settlement concerns later on. So what are we trying to achieve? The main objective, again, in the use of compaction tools or equipment is to reduce the voids within disturbed soil layers in order to assist in trying to bring a soil surface or subsurface back to its normal or natural state before excavation occurred. Now we have to keep in mind, we're not going to get it back to 100%. We're going to try and get it back the best we can. Over the course of time, yes, could it go back to that as weather and the environmental conditions come in, moving those particles back together where they belong. But we don't have all that time on a project. So we have to kind of force Mother Nature back into its natural state, and this is where the compaction tools come into place. So as we look at the pictures below here, we have the air, the water, and the soil components. So off to the left here, we have a disturbed soil sample. We've excavated, we've dug it up, we've broken apart all the solid material end of it or particles, and now we want to get it back to where we're shrinking that down and eliminating the voids that might be present. So the compaction efforts, the evaluation of density as a result of the compactive efforts with rollers and other equipment will provide common quality control measurements on the soils at construction sites. So again, we're looking at what the design professionals have stated as a compaction percentage. We want to meet that, and then we can, once we have met that, then we can start to actually put our structure on top of the soils. The density of a compacted soil is measured and compared to a density goal previously determined in the laboratory test for the soil conditions that are present at the site. So again, once we get to that, what we feel is the compaction level, normally engineers will come out. They'll now take a test on that to see if it has met the requirements. Compaction or compacted requirements are measured in terms of the dry density of the soils. And of course, we always have to remember that the expected values for the soil's dry density will vary with the soil conditions at the site that are required to be compacted. So again, we're not going to have the same soil conditions on the site. We may have some varying soils, so we got to look at that density that we're looking to achieve. And with this in mind, the maximum dry density must be established for each soil type that we have. And for instance, a clay soil may have to be compacted many times and never reach its 2,000 kilograms per cubic meters, while a granular soil may have a dry density above this value and not require compaction at all. So why is water used in the compaction process? And the main reason why water is added to soil during the compaction process is because it acts like a lubricating agent on the soil particles so that these particles can cohesively move back together, reducing the void separations for a tighter fit between the particles. Now, when we look at road projects and we go down and all of a sudden we see the tanker truck there that says water on it, if we look at the back there, we'll normally see some spray nozzles. This is what the lubricating agent is. It's going to run, this truck runs in front of the rollers and sprays the water down so that the rollers can come in and then start to move those soil particles back together. And the soil particles slip over each other and move into a densely packed position, increasing the soil strength and reducing its permeability rate in relationship to the water flow. Again, we always have to remember that compaction is a function of the water content of the soil in question. And a soil with a 0% moisture will only allow for a limited amount of compaction to occur. As we apply more water, better compaction conditions will occur. So again, we're trying to get that water. It's a lubricating measure. So as we lubricate it, it kind of allows the particles to try to fit back together as best we can, eliminating these voids. And of course, this is a direct reflection of the soil particles receiving more lubrication and moving closer and closer together. And here's a typical compaction curve. So we have our dry density on the y-axis. We have our moisture content on the x-axis. We have dry side and the wet side. We're looking for the optimum moisture content. We get the maximum dry density at the top. And we have our zero air void line here that we want to keep everything to the one side of. The maximum dry density, as we just looked at, for a given soil is the dry unit weight increases as the water is added to the soil for compaction purposes. This will continue up until a certain point where a certain moisture content is achieved based on engineering design parameters or standards. Again, we have to keep in mind that beyond this certain moisture content point, the addition of more water will only fill the void spaces between the soil particles with water, and no further compaction will occur or is possible. And the moisture content at which the maximum dry density or dry unit weight is attained is generally referred to as the optimum moisture content. The overall objective of compaction, again, is to force out the air within the soil regions, leaving behind more space for the soil particles to move together and to fill these voids with these soil particles and water. And of course, once we do that, we increase the density and of course the bearing capacity of the standard compaction test With the standard compaction test, soil is compacted into 10 centimeter diameter mold for material that passes the 4.75 millimeter sieve. If coarser materials are used or included with the test, a larger 15 centimeter mold is used. The soil material is placed in 3 layers, and each layer is compacted with 25 blows with a 2.5 kilogram hammer dropping from a height of 30 centimeters. When coarser materials or soil materials are used, the number of blows is increased to 56 in order to maintain the same compactive efforts. In this test, the soil or the sample of soil is mixed with water and then compacted. The mass of the compacted sample is measured, and part of it is taken to dry in order to determine the overall water content that we have. Once this is completed, more water is added to the soil sample and it is compacted again. Of course, this procedure is repeated over and over again until the density decreases. So what we're looking at with the standard Proctor test, of course, off to the left here, we have our mold. The center image shows us the hammer, and of course, the right image shows us the 3 layers that we have made. If we revisit the zero air voids curve, and basically what it is, it's a maximum theoretical density of a soil at various water contents that can be obtained with no air left in the soil-water mixture. And basically we're going to use the equation below, and we're going to look at, and we're going to obtain these points using this equation. So the zero air voids curve line, we're looking at the row for the wet density, which is going to be that rho D, and then we're going to have the row for the wet density, which is going to be that rho W. We're then going to divide that by 1 over the relative density plus the moisture content that we have. And this is how we're going to solve that, and we're going to come up with these points. And there's rules for plotting the zero air voids line for compaction curves. First, no point can be above the zero air void line. This way, no errors are obvious. Second, the slope of the moisture density curve on the wet side of the optimum moisture content is parallel to the zero air voids curve. And this is helpful in sketching the curve when the test results are erratic, of course, which is very common in sand. So again, we revisit the compaction curve with the zero air voids line. We get the wet side. We have our line here, saturation curve, compaction curve that we're looking at. And again, we've got our points, optimum moisture content, and so on. Let's move along here and take a look at the modified compaction test. And because compaction methods and equipment have become more reliable and effective, and loads, as we know, on the roadway surfaces have increased with much more vehicular traffic, a much higher compactive effort is required, and the modified compaction test is now utilized. Similar to the standard test, the compaction effort is provided by a 4.5 kilogram hammer that is dropped 45 centimeters on each of the 5 layers instead of 3 within the mold. The higher the maximum dry density, the lower the optimum moisture content we will have. The maximum dry density of a soil is used in quality control measures. Specifications require a certain percentage of the maximum dry density at optimum water content found by the compaction test for that particular soil. So we want to ensure the density, and we want to reduce the compactive efforts that we may have to employ. So if the soil was below the optimum water content, it may be necessary to add water by spraying. The most important factor required for successful compaction is having the correct water content when we're doing our compactive or compaction process or methods. Field density test, sampling methods. Of course, a sample is compacted or of a compacted material is taken using a method described in the properties of soils presentation. The dry mass of the soil taken is determined, and the volume originally occupied by the sample is measured. The field dry density will equal the dry mass divided by the volume of the sample. And the 2 basic sampling methods are employed when determining the volume of the hole. that the sample was removed from. We look at the balloon densometer, of course a balloon filled with liquid, or a sand cone apparatus. And here are the two right here. We get off to the left is the balloon densometer, and the sand cone apparatus is on the right. So how does the balloon densometer procedure work, or what do we do here? So we take the dry mass of the soil sample as determined and recorded. The volume of the sample hole is found by forcing a liquid-filled balloon into the test hole. A rubber membrane allows the fluid to fill all the cavities of the hole. The volume of the fluid required is measured and recorded. The density is calculated based on the mass and volume recorded data that we have collected, and the water content is then determined. Of course, we can't just put water in the hole, because percolation seepage, the water would slowly give us an error in our values. Sand cone apparatus procedures, again, the dry mass of the soil is determined and recorded. The volume of the test hole is obtained from the mass of the loose sand required to fill the hole. As we know, sand is a uniform medium with a constant loose density that will level its way out and fill the hole. The volume will equal the mass of the sand divided by the loose density of the sand. The density is calculated using the density formula, and the water content determined and recorded. So we can see the two methods we're using. Nuclear moisture density gauge. Advantages, of course, to using this type of test equipment is that the results are available within minutes of use. It also increases equipment efficiency, and you can be pretty much assured that your construction methods are correct. The nuclear moisture density equipment works off the principle that gamma rays are emitted into the soil and are absorbed by the soil based on the soil's density factor. The gamma rays pass through the soil and are measured by a detector, and the density is calculated based on the varying amounts of rays absorbed based on the soil type that we have. And if we continue to look at it, along the gamma rays being emitted, neutron radiation is also emitted into the soil. The neutrons lose energy as they collide with the hydrogen atoms in the soil water. A detector measures the amount of moderate neutrons, allowing the water content to be calculated. Direct transmission mode is used when a hole can be punched into the soil for the readings that we're looking to obtain. The backscatter mode is used when testing asphalt materials, when punching holes into the surface is undesirable. And here's our piece of equipment that we can see. The gauge, we shoot the gamma rays in there and record the information for our density. Let's take a look at the compaction operation and quality control measures. And the following are highway components that require compaction. We look at a subgrade, 15 to 30 centimeters in depth, provides the foundation for the pavement structure to sit on. Fill materials used to bring the soil surface up to the subgrade levels, again 15 to 30 centimeters compacted lifts. We get backfill materials, layers and granular materials used in pavement, and of course asphalt layers at the surface. If we look at the compaction equipment that we can employ, consists of various types of rollers and tamping equipment that comes in the forms of small project compaction vibrators to heavy equipment units. Most of the modern day equipment is self-propelled with compacting wheels equipped to vibrate at a rate of 1,500 to 2,500 cycles a minute for most soils and granular materials. And of course, these types of equipments come with smooth steel drums, drums with pads or feet, or other rubber tires. Heavy equipment units consist of vibratory smooth drum rollers, padded wheel or sheep's foot rollers, pneumatic tire rollers, and smooth drum non-vibratory rollers. We can also use vibrating plates or tampers on our small projects or around areas that cannot be reached by standard compaction equipment. And let's take a look at some of these different types of compaction equipment. Here we have a vibratory smooth drum roller. The next one we can take a look at is a padded wheel or a sheep's foot roller. Continue to look at a pneumatic tire roller. We can move into our smooth drum non-vibratory rollers. And of course, here's our vibrating plates or tampers that we would use on small projects that, again, we can't really get into the areas, so we need some smaller equipment to handle these things. This concludes this Module 2 lecture on soil investigations and compaction requirements. Please take a look at the PowerPoint presentations within the course materials for examples that will allow you or assist you in solving the homework problems related to the different soil requirements and compaction efforts that we need.